Hello everyone, my name is Krishna Ghanta and I am pleased to present our work titled Policies over Poses Reinforcement Learning Based Distributed Postgraph Optimization for Multi-Robot SLAM, conducted under the guidance of Dr. Ramviyas Parasuraman. In this work, we address distributed postgraph optimization problem with multi-agent reinforcement learning. The traditional PGO solvers, like Gauss-Newton, are prone to noisy initial estimates and have high computational overhead over iteration. The RL-based PGO has been shown to effectively correct retractions in the postgraph. Its primary objective is to generate an accurate and reliable initial estimate for downstream optimization. Motivated by recent advances in RL, especially the RL PGO, we propose a multi-agent reinforcement learning approach for 2D postgraph optimization. Given a global postgraph, the objective of optimization is to minimize the error between measured relative estimates and the estimated relative transformations derived from current pose estimate. We cast distributed PGO as partially observable Markov game where each robot refines its local subgraph cooperatively. Each robot uses an edge-conditioned graph neural network with adaptive denoising mechanism to suppress outlier measurements and denoise noisy postgraph edges. A multi-agent reinforcement learning actor applies sequential post corrections through a hybrid policy that leverages both graph embeddings and prior action memory. After all the local optimizations, robots perform an ADMM-based consensus step to reconcile overlapping edges and achieve a globally consistent estimate. This is the overview of proposed method, where we have an edge-conditioned GNN encoder, which consists of the edge encoder, mean aggregation, message transform in the message passing layer. And then we have an adaptive edge gate denoising mechanism, which involves the calculation of a reliability vector and masking. And then we have an action heads in the MARL actor, which perform discrete edge selection to which it needs to update the post, and then the post corrector, which updates the post sequentially. Given a global post graph, we convert it to a local subgraph to feed the robots in a decentralized manner for PTO. Feeding postgraphs directly into the reinforcement learning frameworks might lead to inefficient learning due to irregular and non-Euclidean structure of graphs. For that, we employ graph neural networks to address this limitation by learning node and edge embeddings to respect underlying graph structure. The proposed GNN employs edge-conditioned message passing architecture with normalized mean aggregation, where each edge carries detailed attributes to guide more informative updates while preventing bias from high-degree nodes. The GNNs encode spatial and topological information from Postgres. For instance, the node dimensions consists of the geometric values and the timestamp, and the edge dimension consists of the odometry, loop closures, which can be inter-robot and intra-robot loop closures, and the relative pose estimates, and the information matrices of those measurements, which represents the uncertainty of those measurements. The GNN encodes the graph into latent embeddings with this message passing architecture. The proposed GNN is capable of denoising the noisy edges in the postgraph with adaptive edge-gate denoising module. After each message passing layer, an adaptive edge-gate denoising mechanism evaluates the reliability of each edge by combining its message features, residual error, and covariance cues. Together, these produces a confidence score indicating how trustworthy an edge is. To ensure differentiability during training, the reliability vector of each edge is passed through a Gumbel softmax relaxation, generating a soft mask that allows to learn which edges to keep, which to downweigh without losing any gradient information. During optimization, edges with low confidences are suppressed or masked through sparsity regularization, and at inference time, The system prunes unreliable edges, retaining high quality odometry loop closes while filtering out the outliers. Starting from the GNN learned messages, we extend multi-agent soft actor critic termed as graph-aware stack to handle hybrid action space of distributed postgraph optimization, combining both discrete edge selection with continuous post correction. Each actor is responsible for sequentially selecting an edge to refine and a small pose update for that edge, while a centralized entropy regularized critic evaluates joint actions during training for policy learning. Computation on each robot scales with the local subgraph size, and after iterative updates, inter-robot graph dependencies are reconciled through an information-weighted ADMM consensus process to produce a globally consistent post-graph estimate. The proposed solution has two variants, V1 and V2. V1 is a purely learned solver delivering near optimal post estimates. V2 bootstraps V1 with 75 iterations of classical LM refinement for guaranteed convergence and stability. For training purposes, we synthesize pose graphs for teams 3 to 7 robots, each contributing 60 poses with a 0.15 loop closure sampling ratio under three noise environments modeling noise with varying levels of uncertainty. This picture represents these three noise environments where we have simple, medium, complex. This is the temporal evaluation of the trajectories for the City 10K dataset. We demonstrate the evaluation of sequential edgewise refinement by comparing the inference time and the accuracy in the postgraph optimization. We performed experimentation with three 735 robot sets, and both variants are compared against state-of-the-art distributed PGO frameworks such as CCPGO, MLPGO, and MMPGO. For demonstration, we portray the results in a temporal manner. In this dense scenario, our policy first prunes two-thirds of the corrupted edges, then applies a edgewise corrections, driving the cost down to 4,000 in just 60 seconds, and a 15-fold speed up and 90% error drop. This is the learning. This represents how the learning of the proposed method is. Both panels track cumulative reward in learning, showing raw and smoothened curves that climb from -50 to 50, where negative is a negative reward and the positive 50 is a positive reward. The impact of measurement noise. um, to demonstrate the impact of measurement noise, we have lower noise, which accelerates convergence, while higher noise lags yet still reaches strong final performance, highlighting the robustness to sensor drift. The scalability to team size represents moving from 3 robots to 7, lengthens training, but attains comparable asymptotic rewards, demonstrating that GSAC scales gracefully with additional agents. The proposed framework can produce appropriate initial estimates for the framework where the existing solvers can be bootstrapped with the proposed framework. The AEG denoising module has evaluated on real-world postgraph datasets with controlled injection of outliers by randomly corrupting a fraction of loop closures and inter-robot constraints through large rotation flips and perturbed translations. The proposed variant 1 consistently reduced the global objective by a median of 38% relative to MMPGO, outperforming it in 8 of 9 corruption scenarios with largest improvement of 47% on the T-child dataset in 10% outlier rate. This is the overall evaluation of the AEG denoising mechanism for CT10K dataset. The CT10K consists of a dense web of intra and inter-robot constraints, applying the 25% and 75% thresholds, highlights how the gate suppresses conflict uh, edges while preserving a well-connected backbone. Again, both proposed variants achieve near ground truth alignment, while MMPGO struggles under the weight of noisy starting poses. Together, these results confirm that adaptive educating plus MARL-based sequential refinement deliver robust, scalable, and noise-tolerant distributed PGO. The scalability of the proposed methods was evaluated by replicating actors from 7 to form teams ranging from 1 to 70 actors without any retraining, leveraging agent-agnostic policies that operate solely on local information. Across all the team sizes, both proposed variant 1 and variant 2 consistently achieve substantial lower global objective values than the classical solver, with proposed variant 1 reducing about 15% and proposed variant 2 reducing 32%. This is the overall performance of the proposed method, which is benchmarked with the state-of-the-art method. To conclude, we developed an MARL strategy for 2D postgraph optimization, combining edge-conditioned GNNs with adaptive gating for denoising and post corrections. And this method outperforms existing baseline in accuracy, robustness to outliers, and the scalability on synthetic and real world benchmarks. For the future work, this method can be possibly extended to SE3 postgraphs by adding rotational updates with architectural changes and retraining, and it is also applicable for camera pose estimations in picture from motion pipelines to enhance bundle adjustment speed without sacrificing the accuracy. Thank you for your attention. These are the links for the GitHub repository and the archive paper. Feel free to contact if you have any questions.